ready?
Yeah.
Let's wait for a minute. 1 minute. Good afternoon, everyone. Today we are very pleased to welcome Professor Wenchao from our neighboring institution, Physics Department, URI. And Professor Ge got his PhD degree from University of Texas A&M, right, about 8 or 9 years ago. And he was a postdoc in Army Research Lab at Texas A&M, and then he became assistant professor first in Southern Illinois University, and then I think a couple of years ago went to University of Rhode Island. And that university has a very active program in quantum research. Professor Ge particularly is interested, his research focuses on lots of different areas, mostly quantum information sensing and computation. Today, I think he's going to talk to us about one modality of quantum computing, using trapped ion, and see how he can make things faster, and hopefully it can be better than other modalities. Yeah. So welcome.
All right. Thank you. Thank you, Don, for the introduction. And thanks everyone for coming after a busy day of either in the lab or after class or teaching a class. Thanks everyone for the time. My name is Wenchao. I'm really pleasure to be here, and I'm really proud to to give a talk in this department, which has over 200 years of histories with many notable scientists and many of you, future scientists in the audience. So you may have different backgrounds. You may from condensed matter, you may high energy or particle physics, or maybe astro. But I hope to give you a lecture about trapped ion quantum computing, and maybe make some connections with the things that you're learning. And hopefully you can get a couple of messages after we walk out of this auditorium. I came from University of Rhode Island, and this is our physics building, main building, and in front of the park. And for those who have visited there, and this is the beautiful park. And thanks to our department chair, Professor Leonard Kahn, who recently initiated a quantum information science program in the department, and we have hired 3 quantum information theorists, including myself. So I feel really proud to be here and to be able to join the group over there and for the program that we initiated. Otherwise, I won't be able to present this talk here. And as a loop back, and I would like to mention that Len Kang was once a Brown graduate in the 1970s from the group of Brown Emeritus Professor Si-Chen Ying's group. So my presence here, thanks to Gang for the invitation, and also I feel it's like a feedback that I can to some contribution, giving a lecture and have some discussion with you about my background. So for the research, I would like to acknowledge that my collaborators, in particular, Kurt Hobbs from ARL and Michael Forsback, who is now a scientist at Honeywell doing trapped ion modality with their QCCD system. And experimentalist, I collaborate closely with John Wallinger and Daniel Slitcher, who are leading one on the Penning trap, the other one is leading on a surface trap of Paul trapping. And so without these collaborations, I won't be able to enter into the field and do some interesting theoretical and also collaboration with experimental work. So without further ado, I would like to go this is an overview about the talk I'm going to discuss. So first, I think you all heard, various places from the headline of quantum computing. So there are hypes, but there are interesting things behind it. Maybe we can review that and why we want a quantum computer. Then I will go a little bit deeper on to what kind of physical platforms can be used to build a quantum computer. Then I will focus on trapped-ion quantum computing, in particular with the protocol that we proposed using something called parametric amplification. Okay. A summary and outlook will be given at the end. And during this talk, feel free to interrupt if you have an urgent question you want to ask. All right. So why do we want a quantum computer? Well, so classically, we can use classical computers to solve problems. We can model it. But classical computers may not be efficient for some problems. And for example, if we have like four fuzzy friends who wants to decide what is the best seating options, if given no constraints, then the amount of options are 4 factorial. Okay, of course we know Cooper doesn't want to occupy this position particularly, then that would make it easier. But if we have like a lot of varieties, like if we have 29 physicists who want to find a best solution of sitting in front of this surveillance picture, so that possibility would goes like on the order of 10 to the 30s. So for classical problems like this, or like traveling salesman problems these days, we buy a lot of stuff from Amazon. We have to travel to neighbors. And these are really, really complex problems. And so classical computer may not have the memory to solve certain problems, real world problems. Okay? And at the same time, classical computer have to do things that one after another. Okay? But maybe you have multiple computers, you can do it parallelly, but that's a different story. So that's what classical computers do. But quantum computers, for those who have learned quantum mechanics, we may know that there is superposition and entanglement, which would allows you to encode information into the exponential dimension and to go things parallelly through the unitary evolution. Okay. So that difference makes quantum computer superior in certain aspects. Although that quantum advantage is arguable, but it has the potential to make it faster. So here I would like to quickly review what I mean by superposition. So if you have learned quantum mechanics, then we can find 2 discrete energy levels, and we use those quantized energy levels as qubits. And the quantum bit is different from a classical bit in which it can be in an arbitrary superposition of these 2 states. And it makes it complex and different. And it makes it more complicated and interesting if you have 2 qubits. For 2 qubit states, you could have 4 different bases, and you could have something so-called quantum entanglement. So you have 2 parties that their wave functions, their states are inseparable to each other. Okay, if you measure one state, the other state will be affected, and that leads to even make the greatest scientists in the last century to wonder that it's something like a spooky action at distance. So it's that complicated complexity or sophisticated things that make quantum computing or quantum information interesting. And with more qubits, the dimension will grow exponentially. And with that exponential growth of dimension, you could have many parallel calculations for your encoding your information. And in particular, if you want to represent your system, the number of variables would also go exponentially. And for example, if you have 256 qubits, the number of variables in order to estimate or to represent your state is more than the number of atoms in the known universe. So the quantum system is complicated, and it could provide certain advantages for speeding up. And in fact, there are some algorithms or applications people already know that we could use quantum computers and to speed things up. For example, the famous Shor's algorithm, which can use to factorize or speed up the factorization of integer factorization. And this typically would really, for a classical computer, you would have to go exponential number of time, but for a quantum computer, you could really cut that short. And on the other hand, for the Shor's algorithm, this can speed up the search of finding certain unsorted data. So for example, if you have a trillion data, a classical computer, if you do like one at a frequency of 1 megasecond per search, you would need 1 week to do that. But for quantum computer, if you can have the same speed, if you encode all your data into the quantum computer, you have such a powerful computer, you only need 1 second if you have the same speed. Of course, the time is essence. Classical computers these days can have a much faster speed on the order of gigahertz, but quantum computers maybe on the order of kilohertz or megahertz at most. So one of the ideas that we try to push forward the limit of the field is we want to build faster quantum computers. So these are important relating to other areas like high energy physics. For example, at LHC, we have every second we have 10 to the power of 6 gigabytes of data that is being generated. To search this huge amount of data to get some some properties of our universe requires a lot of calculation. And as you may know, that some areas have already used machine learning or some quantum algorithm try to speed up the search. So that is important not just for AMO physics, but also for other areas. And another area that is also important is doing quantum simulations. So this is like a bottom-up approach. So you build all these atoms or qubits, and then you have them intact and modeling certain, condensed matter models. For example, these IC models, and you can predict a certain features that is not, available or is not achievable in other, from other models that you cannot generate. Some experiments have already been done, but I didn't show a reference here. I learned this year that there is some predictions of high temperature TCs from this bottom-up approach of using certain, some system to do the quantum simulation. And I know that this department has a rich study in high energy and particle physics. For those who do, and you should maybe pay attention to recent progress in trapped-ion quantum computing or other quantum computing architecture, because these can be used to model strongly interacting quantum fields. For example, modeling Dirac equation or the lattice gauge theories. This has been done in certain platforms. So if that's not interesting enough, the strategic side, from government side and from national government, there is a great push forward to this quantum information science and engineering, thanks to the recent development in experiments. And also from the industrial side, you can see this is only a partial list of some of the startup companies in quantum computing, and also some really big tech companies that have their hands and feet into the field. So you can see some of these companies, they have a big portion that they're trying to get involved into quantum computers. For example, like Honeywell, they have a group of scientists they hired, and then they both theories and experiments to do trapped-ion quantum computing. I think also IBM have their superconducting circuits for quantum computers. So, and also from the national support, we have the national different categories of funding on the order of hundreds of millions. And for example, at Brown University, I know you got this quantum idea incubator grant from NSF. And I was very fortunate recently, I got a QIS expand grant from NSF for doing quantum algorithms. So there's a lot of things going on, and I think it's a good time to maybe for those who are not doing quantum, maybe get some ideas of the quantum. I cannot say it will be there, it will be make immediate applications, but it's definitely something that you could pay attention on. So let's look at, if this is interesting, let's look at what kind of physical systems that we could build quantum computers. So again, this is only a partial list. So recently there are other platforms like, there have been these platforms like Code Atoms and also MV centers, all these different platforms. Some platforms are evolving and make it better than the others. And so these NMR and quantum dots are some of the early platforms. And recently we have, in the last couple of decades, we have the superconducting qubits and trapped ions, which have been in the lead. But who would win in the final race, we don't know yet. Because we are far away from have a scalable and really powerful quantum computer yet. So, but my biased opinion is on trapped ion quantum computers. So I'm going to first just give you some ideas of what are the necessary conditions for build a quantum computer. Then I'm going to discuss a little bit on trapped ion quantum computers. To build a quantum computer, Vincenzo has this criteria about over 20 years ago. So basically, you need to have well characterized qubit. So the states, you have to have discrete levels in order to use it as a qubit, and you need to be able to scale them. If you have a couple of qubits, it won't serve as a quantum computer, but you need to be able to scale them up really to the thousands or millions, even more. And we need to have relative long coherence time so that the qubit will not lose its information as we prepare it into some useful states. In order to do quantum computation, we need certain type of gates, in particular single qubit gates and arbitrary single qubit gates and two-qubit entangling gate. And of course, you need to be able to initialize the states into some known states and then measure the state to do the readout. Okay, so for trapped ions, it's a very good platform. It's a very clean platform. Ions are just atoms that lose a couple of electrons, and it has so many different ions, and we have different energy levels that could be used for qubits. So we could have optical, fine structure, or hyperfine, and others. And these ions have been studied for many years, and they have really long and stable coherence. Some of the ions are being used as the most sensitive atomic clocks in this world, like strontium. And they are identical, they are the same, so you don't have to fabricate them. So the experiments done here can be replicated at different places. So in order to trap them, so to have some motional states, so we have internal qubits. The qubits don't generally talk to each other because when they are trapped, they are on the order of 1 micron apart. They have Coulomb interaction, but the Coulomb interaction is too weak to engineer any useful interaction. So we need to use its internal vibrations, motions. So we trap these ions in basically 2 types of traps. So if you have just a static electric field or static magnetic field, you won't be able to trap a charged particle in 3 dimensions. Okay? You might run into some saddle points, but you won't be. So you need either a combination of electro quadrupoles and magnetic field in so-called penning trap, or if you have some dynamic electric field to trap it, it's stable, but it's stable over the time. So we have this trap, we have this motion of the ions. So if we look at just 1 degree of freedom, if we have 1 ion, we would have 1 motion. If we have n ions with the Coulomb interaction and the harmonic trap, they would form some kind of crystals. And so effectively, you would have normal modes for n ions. So n normal modes for these ions. And what we can do is the normal modes is first, without the normal modes, we can use microwaves or optical fields to do single qubit gate to prepare the state in arbitrary single qubit states. And we can shine lasers to couple the motional states to the qubits. So one way of doing this is by shining a co-propagating laser such that you generate some standing wave in the field where the ions are sitting. And then this co-propagating laser, by choosing suitable frequencies, so you will be able to, for example, generate some stark shift. So the stark shift would change the frequencies of these levels, and you can make it in such a way that this energy level are changed proportional to the position, and effectively you can be able to generate effective qubit-qubit interaction. I will show you in a moment how these are generated, but just throw you on the idea that the qubit can be interacted and generate effective two-mode two-qubit gate. And for the readout, this can be done through shining a laser to some highly excited state, and then to have it go through spontaneous emission to initialize the qubit. And for the motional states, experiments has been developed in the last few decades to cool the motion to very close to the ground. And so to read out, depending on whether it is in one state or zero state, we can shine a laser to distinguish the states from the fluorescence results. So the readout can be done very, very accurately. So another thing about the trapped ions is how we can scale them up. And you can probably put like tens ions in here, or maybe 20 in a linear chain. But if you go over that, it may be not realistic. The trap would become non-uniform, and they may have zigzag motions, make it bad to control. So one idea of scaling this up to thousands or millions, this is an ongoing process, is to have this modular idea. So if we have one elementary logic unit of maybe 10 ions, we could have many of them, and then connecting through optical fields to have them interact and talk to each other. And another way of having this type of architecture and to have them scaling up is this so-called quantum charge coupled device. And so this idea is we can design the trap in a two-dimension and having ions in different zones. And depending on what kind of interactions you have, you can just shuttle the ions and prepare them in certain zone and then move them and then moving back. This is in principle possible to scale things up and make it many of the platforms, and then make it more of this different things. And then, but it's complicated. How do you shuttle and how do you connect the ions with different places? So there is it's possible to scale them up, but there are technical details how we can do that. In the field, I just go to recent works, maybe not so recent, but give you some ideas that these ions, for example, with just 5 qubits, one can do this complicated computation. And with hundreds of ions, people can generate really sophisticated entanglement and study maybe some phase transition or condensed matter things, or use them to do quantum sensing. And so this is important. So I would like to just show you that trapped ions has really long coherence time, and on the order of every seconds or even longer, and they are identical. We can see with these properties, we can prepare really high fidelity single qubit and 2-qubit gates. But the ions are limited by certain things to scale their speed up. So the challenges in trapped ions is they are relatively slow comparing to other platforms such as superconducting circuits. And to scale them up, as I argued, that there are some difficulties if you want to do module or do like the QCCD architecture. And I would like to just give you one more slide to argue the challenges. I'm not saying that trapped ion is not useful, but there are things that we could improve. So going a little bit more detail. So the gate time, maybe we want to, let's just consider one thing to improve. Let's improve the gate time, make it faster. How do we make it faster? We need to have stronger coupling. To have stronger coupling, we could use stronger laser. But the laser power may not be, stronger laser power may not be available. But on the other hand, if you have a stronger laser, you crank up your power, but at the same time you realize that, well, there is something else. The laser would also induce errors, because in the most accurate two-qubit gates that people have generated with trapped ions, spontaneous emission due to the lasers would randomly kick the qubits, is the leading source of error. So if you use more lasers, you could have improved the speed, but the fidelity is not improved, and which would limit your ability as you scale things up. And even if you have more ions, as we argue, there will be more motional modes. And if you're increasing the laser power, so you would involve not just coupling to one of the modes, you would also coupling to many other modes and make it really, really complicated. And then you would introduce cross-talking and errors, and a lot of things will go wrong. And so this basically leads to this so-called impossible trinity, the power usage and the gate time and the fidelity. And the question is, can we break this? And of course, we can. And the idea that we introduce to the trapped ion quantum computing platform is parametric amplification. And this idea, as I will show at the end of the talk, it will not only useful for trapped ions, but also useful for many other systems. Maybe it's related to your platform. Maybe you could find applications extended to other things as well. So let's talk about a little bit detail about the theory of trapped ion quantum gates, and then we introduce the theory of parametric amplification. So we want to generate two-qubit gates. Single qubit gate may be trivial. Okay, you apply some pulse, you have to do some Rabi oscillation. For the two-qubit gate is the most important thing. So here I'm just encoding the states in not 0, 0 state, but some superposition state. So this plus is just 0 plus 1. Okay, I write it just to make it mathematically correct when I'm having the unitary evolution. So, but this is just some basis you can consider as for the qubits. And we apply this lasers shining on the qubits. What we have is, I can show you this Hamiltonian. The last two parts are the motional parts. So suppose we just look at two ions, and we looking at the limit of just one motion mode. We just forget about the other motion for the moment. So these two terms describe the potential and the momentum of the ions, and effectively it can be described by some quantum harmonic oscillators. Okay, and the first term is the interesting term where you use the lasers to couple the internal qubits to this standing wave motion. So what happens is you shine these lasers, you would introduce AC stock shift, which would change the frequency of the qubits. So this is basically sigma z, basically describe the energy level shifting. And you design in such a way that the shifting to the spin up is just opposite to the state going down. Okay, so that's why you have this nice form. And we know that AC stock shift is proportional to the intensity of the laser. So therefore, by shining this standing wave, we could have this sinusoidal intensity that depends on the position, on where your ion is. Okay, so therefore, we couple the position to the qubits. Okay, so that's some coupling we have, and we can transform this potential term into harmonic oscillators and expand this sinusoidal term into the first order and get just the linear coupling as we want. Okay, so that is some limit. We call it Lamb-Dicke limit, Lamb-Dicke region. Okay, so in that region, we would have effectively the linear coupling between, say, this is not very obvious. Yes. The linear coupling between this is A plus A dagger. That's basically the position, the linear position of the ion couples to the qubit internal states. So we have this linear coupling. And what this does is you have, depending, you go to certain rotating wave approximation, rotating wave frame, and then in that frame, this would goes some rotation in space for the motional states. And depending on the qubits, on whether it's spin up or spin down, you would have different effects. So if we look at just the one qubit, okay, so if we have it spin, if the state is spin up, so it will undergoes this circular motion for the motional mode in phase space. If it is spin down, it will go different directions. Okay, and after it goes through, it will acquire some geometric phase, and very nicely, then the spin motion and the qubit would separate. So what this is helpful for doing a quantum entangling gate? Well, if you have these both qubits coupled to the motion, and then we could have, depending on the state, we could have different geometric phases, and that different geometric phases would give you an effective unitary evolution that basically gives this sigma ZZ interaction for the two qubits. And if you choose the geometric phases, that is equals pi over 4, you would be able to generate this Bell state-like states, two qubit states. And this geometric phase is proportional to the area that the ion is circulating in its phase space. And it's proportional to the intensity of the light and inversely proportional to the time that it takes for completing the two qubit gate. So we have this effective ratio. So if you want to generate certain entangling gate, say Bell states, the limitation is the laser power, the intensity, and the gate time is fixed. So from this, you can see if I want faster gate. So if I want T to be smaller, I need to have F to be larger. Okay, so that is the fundamental theory to describe this trapped ion quantum gate and the limitations. And we could make this larger by using stronger laser power, but as we argued, when we have stronger laser power, these photons would also randomly kick the qubits and would make this coherence decohere. So when you have larger laser power, you would have greater decoherence. So eventually, you may not win, okay, because you get faster speed, but you don't get a stronger, better fidelity.
A quick question.
Yes.
On the previous slide at the bottom, that equation, so you're going from initial state to a final state, right?
Right.
For the initial state, I guess that's a pure state, I guess.
Right.
But what if you wrote it such that it's a pure state, but a superposition, and maybe the second term has a phase to it?
Mm-hmm.
Would that phase have a physical meaning to it?
Oh, you mean this second term, the phase?
Oh, well, I mean for the initial state.
For the initial state.
Yes. So suppose the initial state, you wrote it as a superposition, but
right.
It's a pure state.
Right.
And one of the terms has a phase to it.
Okay.
Typically, the phase doesn't matter, but we're talking, I guess, these things here, quantum entanglement, would that phase have a physical meaning to it?
Okay, so it depends. If the phase is global phase, just outside the state, it doesn't matter. If it is a phase that is inside the superposition, it could matter.
And so what will be the physical meaning of that phase?
The physical, well, it's just a difference initial state. So
Well, I mean, like, for example, you might calculate metrics like expectation values, correlations,
okay.
von Neumann entanglement entropies, but that phase typically disappears. And so I'm just curious if you give an example of where it would appear.
Well, so if I understand the question correctly, I think the phase, if it depends, if it is some phase, you may or may not be able to generate an entangled state depending on your initial state. Okay. So, for example, if your state is an eigenstate of this evolution, so as it evolves, so it will stay as the eigenstate, so it won't be able to generate. So I write it in this way. So this state is not an eigenstate of that state, so it can be split into a superposition of eigenstates of this state. Therefore, it can generate entangled state. So if you have a phase, then it depends on whether whether it's important or not. It really depends on what kind of phase is, where it is. Okay.
Thank you.
But thanks for the question. Okay, so I would like to introduce you the parametric application. So we waited almost 30 minutes, 35 minutes to come to the meaty part of this. So I hope I have given the background. So the idea is we can have some parametric application. So the parametric application, what it does in experiments is you just apply some oscillating electric field at the end caps of the voltage, and so you just modulate the trap. So you are applying some modulation to the trap. So this is effectively to something called squeezing for those who are familiar. So you have some quadratic terms. So what does is if you don't have a trap, parametric application, if we have this spin-dependent interaction, we could have this just move in space, and then we want to generate some geometrical phases. What the parametric amplification does is you could apply squeezing and anti-squeezing to the state to apply this parametric amplification in resonant amplification. So what it does is it could amplify the displacement in phase of the motional states. And what that helps is this amplification could improve or amplify the geometric area that you created in the same amount of time. So that is assuming if you could apply the squeezing really fast and at certain speed, then you could increasing the amount of geometric area without increasing the gate time. Okay. So, or you can use a relative weaker laser power and then create a faster quantum computing gate. So we did this and with this stroboscopic idea or discrete idea, and with some ideas to do the sensing. This is not necessarily quantum computing, but for the sensing part. For the sensing part, we have designed these protocols. If we applied certain spin states and doing displacement and apply the squeeze or the parametric amplification, we could amplify the signal, and therefore the sensitivity of estimating the displacement is improved by this factor of 1/e to the power of 2r. And comparing to without the parametric amplification, we could, in theory, improve this with 10 dB of reduction of the sensitivity for estimating certain displacement that is sensitive to the trap lines, the trap line that is sensitive to like the electric fields. So this squeezing or amplification can also be used to speed things up. And so in another proposal by Schoenberg and Christian Arntzen, so in their experiments and theory, they used alternating squeezing and anti-squeezing, and also change the phase or the direction of the squeezing and anti-squeezing. So they squash it in along the x direction and amplify it, and then they squash it in the y direction. So the effect of this is they could improve or have the interaction to be fast. Okay, so this oscillation is faster than the red one is faster than the blue one without the parametric amplification. And so effectively, the unitary evolution is improved by this factor due to the squeezing or your parametric amplification. However, there are a few catches of this discrete protocol. So the basic limitation of this one is you would have to have very accurate squeezing and anti-squeezing. You have to cancel your operations. If you don't cancel your squeezing operation by an anti-squeezing exactly, you would have some residual squeezing or anti-squeezing, then that would affect your errors of your accuracy. And that's what relates to the phase matching. And the question is, can we also have another protocol that without worrying about the phase matching? Well, the answer is yes. So we could also have a continuous protocol that we can do this parametric amplification. So the theory of parametric amplification, we can write it down here, is we modulating the potential of the ions that it is sitting. And so we have this time dependence over here and with this square terms. And if we write these terms and drop out those fast oscillating terms which contribute into some corrections, we would have this effective terms that is being added to the original spin-dependent force Hamiltonian of the trapped ions. So that's just some additional terms that we try to add it. And this is basically some squeezing terms. And what this does is we have to combine it with another quadratic term, this detuning term. So the detuning terms, for those who are familiar with quantum optics or harmonic oscillators, the detuning term basically just rotate the state. And the squeezing term will just stretch, squeezing and amplify in one direction and in the other direction. So the combination of this, what does it do? Well, physically, there is a term called Bogoliubov transformation. If this squeezing term is not stronger than the detuning term, we could rewritten this in terms of new bosonic mode with a new detuning. Okay. So effectively, it would undergo some periodical oscillation. So what it does is we can have this picture. So it rotates and squeeze, and then it rotates again and keeps squeezing. And as it rotates, some of the squeezing becomes anti-squeezing, so it cancels and goes back to like original uncertainty. And so it keeps going, squeezing and rotating, and brings back. So all this is a periodical oscillation. So if we're including the first term here, we would have an effective Hamiltonian. What this does is it's very similar to the original Hamiltonian, although it's a little bit different. So in the phase space, it would undergo a trajectory, but it is an elliptic trajectory. So it will go something like that and keep going and going back. So it will acquire a geometric phase. And this geometric phase, with the same amount of time, it could be greater. Or in other words, if we prepare the same amount of geometric phase, we could do it much faster. Okay. So how can we see that? We can map the Hamiltonian to the original Hamiltonian. We see the only difference is we would have a stronger interaction mediated by this Bogoliubov mode, and we have a different tune. Okay, that's it. It's everything else is the same, exactly mapping to the original Hamiltonian by adding this continuous protocol of parametric amplification. And we can see the difference immediately. So without parametric amplification in the continuous protocol, we would have, without parametric, we would have this relation or the scaling of the laser interaction strength and the gate time with the geometric phase, the amount of interaction you need. And with parametric amplification of the continuous protocol, we would have this reduction, 1 over e to the r reduction. Okay. So that is, we basically adding additional tool to the system to make it better. Okay. And so you can see if we fix the laser power, the gate time would be reduced by this factor due to the parametric amplitude. Yes?
What is the R term?
So R term, I'm going to show you that e to the R is defined by this 1 over L squared, and it's approximately equal to the parametric strength that we apply times the gate time you have. So for the fixed gate time, the stronger parametric you apply, the greater enhancement you could get. And at the same time, if you have longer gate time, you could improve this even better. But there is a catch. So you can see these dot lines, but I didn't show you the exact result. This straight lines improvement won't be goes as linear as you wish, but it will be curved down due to additional terms that we dropped out, like the lambda limit and the counter-rotating terms that we have dropped out. So this also tells us this gamma is the decay rate of the trapped ions when you prepare some coherent state or entangled states. So it's proportional to the laser because it comes from the spontaneous emission of the laser. So as you use the parametric amplification, you would also reduce this. If you fix the gate time, you would be able to reduce this effective, using a weaker power laser to generate the same gate at the same time. Okay, so how much time do I have?
Maybe another 5 minutes.
5 minutes? Okay, so I think I'll just show you one example and one experiment in 5 minutes, and then let's come into the conclusion. So suppose we have a 5-ion string, and that is useful in some elementary logic unit if you want to scale it up. And with 5 ions, we would have 5 motional modes. And if you do, the theory tells us if you try to just apply a laser to it, and you won't be able to have all the motional modes to disentangle with your qubits. You would have some residual entanglement with this mode or that mode. And so this would introduce errors because your qubits is entangled with the motion and it's not clear system. So we did some numerical analysis in our paper that we see that in the case of this 5-ion, we give their spacing, their motional modes, we modeling the system, and if there is no parametric amplification, this is the amount of laser that is required to generate the gate. If we fix the gate time, as we can see, we would have some amount of laser power that is, we normalize that. And as we increasing the parametric amplification, we see this laser power is reduced. At the same time, the gate fidelity is improved because the laser is induced, the coupling to this unwanted modes is effectively suppressed. Therefore, we improve the fidelity of building a 2-qubit gate in this 5-ion string. But you can view it differently. If you fix the laser power, then as you increasing this parametric amplification, you would expect the gate time to be reduced. That is, I'm going to show you in this experiments that my collaborator did in Nesta Boulder, also from University of Colorado Boulder. So what they did is they basically did a 2-qubit gate in a magnesium of magnesium ions trapped in a surface trap. And what they did is they calculate the speed time to generate 2-qubit gate, and then they apply the parametric amplification to modulate the trap. And they find as they increasing this parametric amplification, the speed, the enhancement of the speed or the 1 over inverse of the gate time is improved, and with a maximum improvement of about 3.8, I think. And at the same time, if we can see this curve is showing that the fidelity of the 2-qubit gates that is being generated as we apply this parametric amplification. Although we see the fidelity is being reduced because the parametric amplification is sensitive to frequency fluctuation. So if you have frequency fluctuation, it would affect the ability or the accuracy of your control. But if the system, we make some artificial system, if the system has really large qubit decoherence that is not related to the motional states, then you could actually improve the fidelity of that because you are doing a much faster gate. So this graph is just showing the platform, the protocol is stable if you have a different phase alignment between your laser and the parametric drive. With that, I think I am concluding. So the parametric amplification is very useful. We tried it on the trapped ion system to improve the gate time and the fidelity in certain situations. And this also has been studied in other systems because this belongs to a generic boson-mediated system. For example, if you have cavity fuse with atoms, these atoms are mediated by the cavity fuse, or in some superconducting circuits, you have microwave, this LC circuit, mediating certain interactions, or in optomechanical systems. And this one is more related to condensed matter, where you have the electrons, the superconducting effects mediated by the phonons inside the materials. So with that, I would like to conclude that trapped ion quantum computing is a pristine platform, and although there are gate time and challenges in scaling up, so we propose a theory and an experiment to do this parametric amplification to enhance it. And this also opens new paths to promote the trapped ion quantum computing. And with that, I'd like to thank you very much for your attention and welcome to any questions.
Thank you. Questions? Yes.
So in the last 5 years or so, I mean, there's a new approach to do quantum computing by using neutral atoms for looking and Harvard and other folks. So what's the benefit and downsides of using that approach compared to trapped ions?
Okay, so you should not ask me that question because I'm not doing neutral atoms. You are giving me, a trap for me to jump in. No. Well, but I can. Well, I showed you I can talk about the benefits of using neutral atoms. Okay. So neutral atoms. What I know is recently there is a trend using optical tweezers to trap neutral atoms, and the benefit of that is you can very easily, you can have really high focus optical lasers, and you can trap so many hundreds of them, and then you can move them around. You tweezer them, you just grab them and move them around in space. So this is very convenient. So it has been studied a lot in a few places. So that's something I know about.
So with parametric amplification, is it gonna speed up gate time, or is it gonna improve memory error? What exactly is it gonna increase? And do you need your ions to remain coherent for a long time, or is I understand that in trapped ions, dephasing or them fading into other states is a big problem right now. So would this help with that, or would that be a limiting factor for this?
Okay, so this will not affect it's dephasing or decoherence because it's something you apply while you have the interaction. So basically, you are speeding up the interactions of the qubits.
The interactions?
The interaction. You speed up the interaction, so you improve the time.
Okay.
Yeah.
Thanks.
Yeah. Cool.
So maybe you have showed this, but what is the upper limit of this acceleration?
The upper limit? Okay, yeah, that's a very good question. So I probably don't have it here. Maybe I have some supplementary slides I can show you. So if we including all the terms, like the rotating wave terms that we have throw away, the Lamb-Dickey approximations, if we have including all these different terms, then the enhancement is not as linear as we wish. So it will curve down. So you can see, depending on the gate time, you may have different enhancement. So this basically tells you e to the power of 2r. I would say if you have like 5 times enhancement, 5 times to the speed, then it's possible. And we have demonstrated like 3.8 times enhancement to the speed in the experiment. Yes.
Does the relative phase between the spin-dependent interactions and the parametric amplification affect the geometric phase, and does it like somehow come up and you implement these experimentally, the schemes?
The relative phase
Between like the spin-dependent, so you have a spin-dependent force between the ions, right? And you're applying your amplification scheme. So does the relative phase between them affect the overall geometric phase that you're trying to generate?
Okay. Yes. So there is. Let me see if I have it here. Yeah, I don't have it here, but it's okay. So the phase depends on different, the phase alignment of your parametric amplification and the spin-dependent force. You could have parametric amplification or de-amplification. So probably I can show you in one slide, maybe. Let me see. Okay, so here you can tell that if my G is not phase aligned, it becomes completely phase anti-aligned, becomes minus G. If I add 180-degree phase, you will see this enhancement. It will very poorly become delta minus G and delta plus G. Therefore, it will become de-amplification.
Okay.
Yeah, it will make it slower. But this won't happen because most of the phase stability of the experiments is very good. It can be on the order of like 15 degrees. Yeah.
Right. Gotcha. Thank you.
Yeah. But thanks for the question.
Does low temperature, cryogenic temperature make things faster?
Well, cryogenic temperature will not make it faster. So most of the trapped ion experiments cryogenic temperature is not required. Some experiments, they use cryogenic temperature for certain reasons. Typically, these motions, they may be affected by the temperature thermal noises, but they can be cooled down to the ground states so that you don't have to worry to use a cryogenic temperature. But you do have to make it cool down to the ground states.
You mentioned a little bit. Could you talk about the application of this trapped ion method to metrological application?
Okay.
Like quantum sensing.
Okay. Yeah. So there are a few things people can do. So maybe I can bring to that slide. And so one thing that we are really interested is these ions. They are really sensitive to electric field. So we can map the signal if we have certain displacement. The electric field would couple to its motion and just give it a force and push it. And we can map the signal to the qubit states and read it out. And it's argued that when we, with hundreds of ions, and especially if you prepare some type of entangled states of the qubits and the motion, then you can improve the sensitivity. I forgot about the sensitivity, but it's basically very close to the limit to detect certain dark matters. So this is a very interesting field where you can apply, transfer the signal into the qubit phases and then read out through the qubit phase.
I see. Yeah. And you mentioned this can be applied to other modalities such as superconducting quantum device and also code added.
Right.
Has this been used for those two?
For those two, experimentally, I don't think so, but theoretically, there are a few proposals that, depending on the specific platforms, they could apply some kind of parametric amplification they generate, and then in combination with system platforms, they could improve the fidelities, the speed of the system.
Thank you.
Yeah.
Any other question? If not, let's thank our speaker for this wonderful talk. It's very good. Yeah. Yeah, I think it's very good.
Yeah.
Because I noticed in this department we have different things.
Yeah, during
Okay. I have an independent study on quantum sense, and there is a way. Actually,
Hey, how are you doing? Hey, Dr. Yeah.
Hey,
I should
hello.
introduce myself.
Yeah.
My name is Lee Gu. I'm a professor at CUNY.
Oh, really?
Yeah.
Okay,
But I live
okay.
in Providence, so sometimes
Okay,
I go to
okay.
conferences.
Yeah. Nice meeting you.
Nice meeting you.
CUNY, right?
Yeah.
Okay.
So I actually even play soccer with some of your students.
Oh, really?
Yeah.
Okay.
Like Guayang, but that was quite a few years ago.
Yeah, Guangyanhe. Okay.
Yeah.
So do you commute?
Yeah, so I most of the time go to New York on Monday and then come back on Wednesday.
Oh, okay.
Yeah.
You also in quantum computing?
A little bit. I mean,
little
not
bit.
so much. Yeah, so for now we do flying, what do we call that? So it's not qubit. So for now
Okay.
we have 4 superposition of studies there
Yeah.
too. Yeah. So we had a paper. I mean, that's in the classical regime, Nature maybe like 4 or 5 years ago.
Okay.
And this year we finally push it to the quantum limits.
so he has done a lot of great work. I learned a lot.
Okay. I'll look you up. Yeah. So I'm in the physics department.
Yeah, of course. I
And
knew you, so for now. Just I have
Yes,
never
brother.
introduced myself to you.
Yeah. Okay.
Yeah.
Now we know each other.
Yeah.
Yeah.
Yeah. So I was going to say that we have another protocol that we could even improve 20 dB reduction for the displacement sensing. Let's maybe push this to the limit of detecting some dark matter.
Okay.
Yeah. So I'm currently working on that.
That's great. Yeah.
So I didn't even know about your talk until yesterday. I was
Oh.
just passing by the hallway and I saw the poster. I said, why not just drop by?
Oh, are you on our department email list? And
No, I'm
we have a
not.
newsletter. Yeah.
No, I mean, I'm not really affiliated with Braun. I mean,
We can send it to you because
I mean,
you are local. Yeah.
yeah. So also, actually, Gigi Fan was a classmate of mine at Yale. So
Oh yeah.
Yeah.
Okay. All right.
so
yeah.
Gigi Fan is one of their faculty members.
Okay,
She's
okay.
an astrophysicist.
Uh-huh.
Yeah. Oh, yeah.
Phenomenological.
Phenomenological high energy physicist. Yeah.
Okay. Yeah.
So for you, it's also close, right?
It's
like,
close.
40
It's
minutes
40
drive.
minutes drive from my school and from my home, like 30 minutes.
Yeah. I actually even met one of your students during one of the Gordon conferences this summer.
Oh, really?
Yeah.
Who is the student?
The guy who also plays soccer.
Is it Paul?
Kind of tall.
Oh, okay, Garrett.
Yeah,
Garrett
maybe
Jepson.
Garrett,
Yeah.
So why were you there for the Gordon conference?
I was not there.
Yeah, I just wondered. It's quantum computing and stuff. Right?
Oh, yeah. I have other
Yeah,
things to
okay.
in Newport, right?
No,
Not
this
or
was in Stonehill College,
Boston.
close to Boston.
Close to Boston. Okay. Yeah. Yeah.
Very nice. Yeah. Okay, so I assume you have some arrangements, so I'll just get out of your way.
Okay. So
Yeah.
we'll
Nice meeting
reach
you.
out. Yeah.
Yeah. Thanks
Nice
for
meeting you.
coming.
Yeah.
No problem. Yeah.
Do you use this for quantum information also?
Use what?
This technique
This text.
for quantum information generation and transmission stuff, or is it very different?
It's so basically for quantum, I think so this speed up of interaction could be used for quantum sensing,
Quantum sensing,
quantum
yeah.
computing.
Yeah.
But for quantum communication, I'm not sure.
Not sure. Okay. You just turn this off.